So now this time we're thinking about momentum and impulse. So we'll start with uh, a definition of momentum, using P as our algebraic symbol for momentum since M is already taken. Uh, Momentum is a vector, and it's just a product of a plane number, mass, times another vector, velocity. So anytime you multiply a vector times a plain old number, in other words, multiply it by a scalar, you get a new vector in the same direction as the old vector, but with a different magnitude. We've been thinking a lot about forces, and what forces do is cause acceleration. In other words, they make the velocity change. So, of course, if the velocity changes, momentum will change also. So, let's just write out the change in momentum. It's final momentum minus initial momentum. Notice that I'm just keeping mass the same here. Momentum could change by changing the mass. There are cases where that happens, but for now we'll just simplify things and say that the only momentum change, it comes about by a velocity change. So collect the mass terms, and then I've got mass equals the quantity final velocity minus initial velocity, but final minus initial is always what we mean by the change in something. So change in momentum is just mass times change in velocity. We're interested often in the rate at which velocity changes, in other words, acceleration. So we can think also about the rate at which momentum changes, and that is we'd get that just by dividing this equation by delta t, where delta t is the amount of time it took to get this much momentum change, and that's the same amount of time that it took to get this much velocity change. Well, we've seen this before. Change in velocity divided by the length of time it took to make that change. That's acceleration. That's our definition of acceleration. And mass times acceleration, we've seen that before. Newton's second law, that's the net force acting on an object. So, putting it together, this equals this. In other words, the rate of change of momentum change divided by the length of time it took to make that momentum change, equals net force. That's really just a different way of writing Newton's second law. Aside from defining a new quantity, momentum, we haven't added in anything that we didn't already know. Just a bunch of algebra, and then our definition of acceleration, and then Newton's second law. But we can rewrite this, and if we rewrite this, it allows us to see some things that we might not have noticed otherwise if we were thinking only the old way about Newton's second law. So multiply the whole equation by delta t, and that cancels out the delta t in this denominator and adds a delta t factor over on the right-hand side. So we've got now change in momentum equals net force on the object times the length of time it took to make that momentum change. But of course, that momentum change happened because this net force was acting. So we can also say that the length of time here is the length of time this force was acting. Because as long as this force was acting, velocity and momentum were changing. And so change in momentum is happening as long as the force is present. So you can think of this as the length of time in which the force was acting. And as I said, we see some things here that we might not have noticed otherwise. For instance, this is the idea behind airbags. So you're in a collision, and you come to a stop suddenly. That means your momentum changes, right? That means your final velocity, of course, is 0, and your initial velocity is something other than 0. So your change in momentum is the final momentum minus the initial momentum. But of course, the final momentum is mass times final velocity. You've come to a stop, so the final velocity is 0. So your change in momentum is just minus the initial momentum. It's a loss of all your initial momentum. The change in momentum just amounts to your initial momentum all being subtracted away. So this change in momentum is caused by a force acting for a certain amount of time. That's equal to the net force times the time that net force is acting. And basically there are two ways that this could happen. No matter how you're brought to a stop, the momentum change is the same all the time. It's a loss of all of your previous momentum. And that can happen basically in two different ways. It can happen by a big force acting over a short period of time, or it could happen if a more modest-sized force is acting during a greater length of time. What happens when you come to a stop, whether you hit the steering column or hit an airbag, you don't stop instantly. You're brought to a stop over a short period of time. And the steering column is hard. It doesn't have much give or flexibility to it. It doesn't get squished very much at all. So it brings you to a stop very quickly. In other words, in a short amount of time. So if the time is small, then the force will be larger in order to get the momentum change that you know is going to happen. An airbag, on the other hand, has a little bit of squishiness to it, not a lot, but just enough so that it brings you to a stop more slowly over a greater length of time. And therefore, you get the same amount of momentum change with a smaller force acting on you because it's acting on you over a longer time period. And the smaller force acting on you, you're less likely to get seriously injured. Let's think about something else here. We're thinking about forces acting for a certain length of time, so we can represent that kind of situation with a graph of net force versus time. And let's take a simple case where it's a constant force with a value of F newtons acting for this long, from some initial time to some final time. from some initial time to some final time, and so there's a change in momentum. The change in momentum is just that net force acting that long. Like this length of time here is just Tf minus Ti, or the length of time that the force was acting. But notice delta T is equal to this length on this rectangle, and net force, F newtons in this case, is just equal to the height of this rectangle. So force times time is just height times length of this rectangle. In other words, it's the area of the rectangle. And now we've got a relationship between some significant quantity, change in momentum, and area in a graph. We saw that once before, way back in chapter 2, when we saw that in a graph of velocity versus time, there was an area that was equal to the displacement of the moving thing. And here, very similarly, in a graph of net force versus time, the change in momentum is simply equal to the area between the force line and the time axis. And that's true not only in this simple case like this, that's true no matter what the force line looks like. If the force behaves like that, it's still the case that the change in momentum caused by that force is equal to the area between the force line and the time axis. One little tweak we have to make here, in case that force is negative. Let's imagine a negative but constant force of minus F newtons, and constant force that acts from some initial time until some final time. And because there's a force acting on the thing, there's going to be a change in momentum. And the change in momentum is just that force, which is minus F, times the length of time that force was acting, this much time, final time minus initial time, or delta T. But again, this number is equal to the length of this rectangle, and this number, just plain F, the magnitude of this negative force, the absolute value of this negative force, is equal to this length. So this length, F, times this width, delta T, F delta T, that's the area. So in this case with a negative force, the change in momentum is equal to minus 1 times the area. Right? Area was just F times delta T. So just to summarize our rule here, in a graph of force versus time, net force versus time, if the net force is positive, then the change in momentum that force causes is just equal to the area between the force line and the time axis. And if the net force is negative, that implies that the change in momentum is equal to -1 times the area between the force line and the time axis. Okay, now one last thing here about terminology. We have our rule here. Net force times the length of time that force is acting equals change in momentum. We have another name for this kind of thing. We often call this product of force and time impulse. And algebraically, the book will usually refer to impulse with the algebraic variable j. But whenever you see the word impulse or see the algebraic symbol j, that always means this product, and it also means the change in momentum, because this product is equal to the change in momentum. Whenever you hear the word impulse or read the word impulse, you should remember that word means both change in momentum and this product of net force times time. Okay, let's look at an example of how all this stuff works. Let's say I'm hitting a tennis ball, and the ball starts out moving in the negative direction, and then after I hit it, it'll be moving the opposite way in the positive direction. So its initial velocity, let's say, is minus 15 meters per second. And let's say we don't know the positive velocity, the final velocity, after it's been hit. But we can figure that out if we have the right kind of information. One thing, we need to know the mass of the ball. It's about 60 grams, which would be 0.06 kilograms. And we know what the force from the racket on the ball is like. We're able to draw a graph of force versus time. And the force is going to be a positive force. So the ball was coming this way in the negative direction, and I'm hitting it this way, so it's feeling a push in this direction from the racket, a push in the positive direction. You can think of it as a normal force from the racket. Right? The racket is basically vertical, and it's pushing horizontally on the ball. And let's say the force from the racket on the ball behaves like this. Not constant, but it increases for a while and then decreases for a while. And let's say that the time that the ball is actually in contact with the racket is, say, 4/10 of a second. That's actually longer than what really happens in tennis, but we'll go with that number just to keep things simple here. And let's say that the maximum force from the racket on the ball is 8 newtons. We're trying to figure this out. This thing, of course, appears in our equation for delta momentum, delta P. Delta P is, of course, final momentum minus initial momentum. We know that number and that number. We know that number. That's the number we're trying to figure out. So if we knew this number, then we'd be able to solve this equation for the final velocity, and we do have a way of finding this number. We use our area rule, because here's a graph of net force versus time, and that rule tells us that the change in momentum, also known as impulse, is just equal to the area between the force line and the time axis. Now notice one thing here. I label this axis net force, but the only force that I'm actually talking about here is the force from the racket. I'm using the so-called impulse approximation. That is, for the short period of time when the racket is in contact with the ball, the force from the racket on the ball and the force from the ball on the racket are the only significant forces. They're stronger than any of the other forces. So to a good approximation, the force from the racket on the ball is the only significant force on the ball, so it's the net force on the ball. Okay, so that area between the net force line and the time axis is equal to the change in momentum, delta P, and that area is triangular shape. So delta P is just that area, and use the formula for area of a triangle, which is 1/2 times the base, which is 0.4 seconds, times the height, which is 8 newtons. And then you do all the multiplication there, and you come up with 1.6 what? Newtons times seconds. 1.6 newtons times seconds is a change in momentum. And as you've seen in the text, the normal unit label for a change in momentum is mass times the velocity, kilogram meters per second. So it turns out this thing here, Newton seconds, actually is an equivalent label to kilogram meters per second. You could call this impulse 1.6 Newton seconds or 1.6 kilogram meters per second. Either one, they're the same. But in any case, we know that that's the change in momentum, 1.6 kilogram meters per second, and that being the change in momentum, it's just equal to this. Final momentum minus initial momentum. And let's factor out the m. So we're left with final m times the quantity final velocity minus initial velocity. And then we just put in the numbers. 1.6 kilogram meters per second, and then the mass is 0.060 kilograms, and that's times the quantity V final, which is what we're trying to find, minus V initial. The initial velocity was 15 meters per second in the negative direction, don't forget the sign, so minus the initial velocity, which is minus 15 meters per second. So inside this parentheses, you really have V final plus 15 meters per second. And then solving for V final, first divide both sides of the equation by 0.060, and you got 1.6 kilogram meters per second divided by 0.60 kilograms equals V final plus 15 meters per second. And notice when you treat unit labels just as if they were algebraic variables, this kilograms cancels out this kilograms. So the number that you're left with has a unit label of meters per second, just the way it should, because what you have on the other side of the equation are velocities, things with labels of meters per second. Sorry, that's 0.06. Okay, and then when you do the algebra, the final velocity that you'll come up with is about 11 2/3 meters per second. We'll round that to 12 meters per second. That's how it all works. The rest of what you do, it will be thinking about some of the implications of the impulse equation, and some of those implications are a little tricky. Take some careful thought, and dealing with tricky things and careful thought is what the class meetings are for.